here first. Do you have anything in particular you want to have questions about when it comes to the conjugated dienes or anything at this point, or we can jump into new stuff?
I don't have any questions yet.
Okay. Well,
We haven't really gone into the.
don't worry, this is the tricky part. So,
Okay.
all right, so these are called this class of reactions is called pericyclic reactions, and dienes wind up being one of the more significant reactions. And this is one of those ones that basically when you take a standardized test that has organic chemistry as part of it, so either a science GRE or MCAT or anything like that, the Diels-Alder always shows up because it's sort of the quintessential pericyclic reaction. There it is. Okay. And so it's the Diels-Alder reaction is the one, is a cycloaddition. We'll talk about basically it's a pericyclic reaction if it doesn't go through an ionic intermediate or a radical intermediate. So pericyclic reactions tend to have a lot of electrons moving at the same time. I would have to go back and actually check the definition, but our oxidation where we started with the peroxy acid and it had like 5 arrows all going at the same time.
Would that technically?
I think it would be because it doesn't go through a radical or an ionic intermediate. All those bonds are breaking and forming at the same time. So I think technically that fits our criteria for a pericyclic reaction. And generally speaking, though, they fit into one of 3 categories. Cycloadditions, electrocyclic reactions, and sigmatropic rearrangements. Right, so cycloaddition is what we're going to spend the most time on because again, that's that Diels-Alder reaction that shows up on every standardized test. And because they actually is the one that if you look at these other 2 examples, all 3 of these categories have 3 arrows happening at the same time. But the cycloaddition is the one where you actually get noticeable difference in product. If you look at this electrocyclic reaction, it's starting with 3 pi bonds and ending with 2 pi bonds and 1 new sigma bond. So basically we converted a pi bond into a sigma bond. And in this case, a lot of these electrocyclic reactions wind up being within the same molecule. So we don't actually add anything to the molecule, we're basically rearranging where the electrons are. And same with sigmatropic rearrangement. Sigmatropic rearrangement, we actually wind up with the same number of bonds, pi bonds and sigma bonds at the end as we started with. So it is a rearrangement, and it's not one that has a huge push towards thermodynamically towards the products. Basically, the only time we see this having a significant effect is if we can rearrange our pi bonds and our sigma bonds so that we get more substituted alkenes. Because remember, alkenes are more substituted or more stable. So that just gives us a way to sort of like doing a methyl shift with a carbocation to get the more stable carbocation. This allows us to rearrange our alkenes to get more stable alkenes if it's a large enough molecule and everything's set up just right. But the cycloaddition is the one that actually has the biggest drive thermodynamically, because it does have, we're going to sacrifice 2 pi bonds to make 2 new sigma bonds. So that's actually a bigger net gain in terms of stability. All right, and so the classic cycloaddition is that Diels-Alder. Hit yourself. And it's also called, so it's named after the 2 scientists who you know, I don't know, popularized this rather, but first studied it in detail. It's called a 4+2 cycloaddition. which seems like we might be talking about carbons. Because we start with 4 carbons on one side and 2 carbons on the other, but it's actually referring to the electrons. We had 4 electrons coming from one of our molecules, then 2 electrons coming from the other molecule. So it's similar, but it means that this applies to larger than just 6
So
carbons.
you're just looking at the pi bonds.
Right.
basically, yeah.
Yeah, exactly, and so what, we only really see this Diels-Alder reaction with conjugated dienes. And then you have to have something that's called, they refer to it as a dienophile, basically whatever's gonna react with your diene. Right, and the net result, it's always the same movement with these electrons. One pi bond from the diene goes to make a new sigma bond. The pi bond from the dienophile goes to make a new sigma bond. The other pi bond moves over, just sort of like a resonance structure. To be in between the 2 carbons that were part of a pi bond, but now the pi bonds are breaking. All right, so the net result is costs us 2 pi bonds, but we gain 2 sigma bonds out of it. So it looks a little different than what we've seen before, but it's actually a little bit simpler than that oxidation. It's only 3 arrows, it's always 3 arrows, and you can draw them either direction. Either the arrows are all moving clockwise or all moving counterclockwise, but you have the same net result either way. But as with most things in OChem, the devil's in the details.
Right.
And actually, it's where it's the stereospecificity that gets a little bit tricky here. Because we don't always see a racemic mixture.
Right.
When we have stereo centers. And this one only has 1 stereo center created, but it's pretty easy to have 2 different stereo centers created if you have 2 different substituents on your dienophile. And so trying to keep track of what specific isomer we get gets a little bit tricky.
So the X, does that just signify a halogen or could it just be anything?
Anything, basically any pi bond that's not an aromatic. Like we won't see this benzene acting as a dienophile, but any pi bond basically.
Okay.
Yeah. So alkynes, even sometimes, if this happened with an alkyne, we would still have 1 leftover pi bond here because we only reacted 1 of the 2.
Okay.
But we see, and we actually even wind up with conjugated dienes can actually react with themselves. Because to go through this process. We have an example of that in the next slide or 2. All right, and just so we're all on the same page, I'm going to reiterate for Christelle and David, just so we're all using the same language. The new material that we have left to cover is what are called pericyclic reactions. And pericyclic reactions just means that they don't go through an ionic intermediate and they don't go through a radical intermediate. So they're kind of a new class of reactions. And they tend, since they're not going through these radical or ionic intermediates, they tend to involve a bunch of arrows happening at the same time. So the example that Jerry and I were talking about is our oxidation, where we started with the peroxy acid that had 5 arrows all happening at the same time. That's an example of a pericyclic reaction. But the classic one, and this one is one that's worth paying attention to because this is the version of a pericyclic reaction that shows up on every standardized test that has OChem. So GREs, MCATs, anything where you're supposed to have taken OChem first, asks about the Diels-Alder reaction. Right, and as the 3 categories that we see for these that we're going to study is cycloadditions, is where we'll spend most of our time. And cycloadditions tend to be, if you have 3 pi bonds, you can turn 2 of those pi bonds into sigma bonds, which are more stable. So that's downhill in energy. Electrocyclic reactions, if you have the right molecule with the right pi bonds all lined up, you can wind up turning one pi bond into a sigma bond, and a lot of times those happen within the same molecule. And same with sigmatropic rearrangement. Sigmatropic rearrangement actually has no net change in the number of bonds. You still have the same number of sigma bonds, same number of pi bonds, but sometimes that can be an advantage to rearranging them so that you get more substituted alkenes as a result. All right, and so this Diels-Alder reaction is our classic cycloaddition. It's always going to be a diene a conjugated diene reacting with another pi bond, and that other pi bond is referred to as a dienophile. All right, so we can draw a potential energy surface for this. And this one, it's simple in terms of potential energy surface. If it doesn't go through an ionic or a radical intermediate, then it's going to be, for the most part, a concerted reaction, which means one step. Which means drawing the mechanism is pretty easy because it's only one step. You just got to remember to draw your arrows all going, moving in the same direction. And it also means it's relatively reversible. So the reverse reaction is called the retro Diels-Alder. Retro means backward, right? Reverse. And basically the Diels-Alder reaction, the forward reaction, is favored at low temperatures. And the reverse reaction is favored at high temperatures. Why would that be the case? Entropy. Anytime temperature is going to play a big role in favoring one side versus the other, we can almost always tie it back to entropy, right? So at high temperatures, we favor the side that has two distinct molecules. Low temperatures, we favor the side that only has one molecule, but more sigma bonds, because sigma bonds are more stable than pi bonds, even conjugated pi bonds. All right. So we do also, it turns out this mechanism is worth thinking about a little bit. And one of the reasons we prepped this by talking about the orbitals in conjugated dienes is because we do see some stereospecificity. So we start with the X can be anything really, just anything that's not a hydrogen, so we can tell apart. If you put your dienophile starts cis, your product will be cis. We're making this new cyclo group. This is one of the reasons why we can be pretty certain that it's happening in a concerted way. It can't be happening through a intermediate, because if we made one of these sigma bonds without making the other one, then it would be free to rotate. We should get a mixture of stereoisomers. So the fact that we don't tells us something about the mechanism. So as practice here, what would the transition state look like? So we're drawing new bonds. How are these bonds going to have to work? If it's pi bonds, they're all reacting. Then think about what the orbitals look like. The pi bonds themselves. What do they look like?
Kind of like the pi bond of benzene.
Kind of like the pi bond of benzene, right? Yeah, they're
Just
above
like
and
the
below.
note, it looks like little like dashes to kind of show that there's such.
Exactly. So if we start with our conjugated diene being flat in the plane of the board, these pi bonds are going to be coming into the board and out of the board, right?
Mm-hmm.
And if we then bring our dienophile in from on top of the board, the dienophile also has a pi bond that looks like this cloud above and below, right? So if we're trying to make new sigma bonds out of pi bonds, we need them to overlap. Basically, if we're trying to make new sigma bonds, this pi bond needs to overlap a little bit with this pi bond, right? And same with the other side. So basically, because we're starting from a planar pi cloud and our dienophile can either approach from above the pi cloud or below the pi cloud. But it has to be approaching from the same side of the ring. It has to kind of dock, I guess. You need it to come set down on top of your pi cloud. And we then remember that we have these substituents attached to it. If this dienophile is going to come in and lay down on top of this, both of your hydrogens, if it start with your hydrogen cis, when you make your new pi bonds, your hydrogens are still going to be cis relative to each other, right? So if the hydrogens are my forefinger, my thumb, when I come bring this in and set it down on top, they're still going to be in the same direction. And the X's are still going to be in the same direction as well. So regardless of whether it approaches from top or bottom, it has both carbons are tied together because they're bonded with this pi cloud, which means these substituents are locked into place as well. Right, so the net result of that is if you start with your dienophile being cis, your product will be cis. If you start with your dienophile as trans, your product will be trans.
And in both cases, you make a 50-50 mixture if they were to be.
Right. And so this one won't have an enantiomer.
Right.
Because it's, what's that term? When it looks like there's a stereo center, but it has an internal mirror plane. Remember what that was called? Meso.
Oh, mesocompound. Yeah.
Mesocomp. So basically, if X is the same in both of these, then we and it's cis, then we make a mesocompound, and the opposite enantiomer is really the same molecule. If X is not the same as the other X, then we would get a both enantiomers, but they would both be cis in each case. And so maybe it would make more sense if we call this is mesocompound, but if we call this a Y instead of an X. If it's two different things, then we can tell the difference. We don't have that internal mirror plane, and then we can say plus EN. And in this case, if they start out trans, then we don't get them internal mirror plane either way. Yeah.
Unless the molecule left is symmetrical. That is my, like if there was, instead of a hydrogen attached to one of the middle two carbons, if there was like a Z, yeah, that one, right?
We'd still, that one's not really changing. Those middle two carbons they're part of a pi bond either way. But even without that, this is not symmetrical. It looks symmetrical.
Yeah.
But it actually does have stereo. If you try to flip it like a pancake, you don't get the other version of it. You'd wind up with the bottom one back and the top one forward again.
Right.
So think of it like a propeller, a right-handed propeller.
With the CHM222 would be different, right?
It is different already if you flip it.
Yeah.
So this is different
Oh,
than
yeah.
than this one.
I see. Yes, the others do not.
Because it doesn't superimpose. And again, when it's something like this, where it looks like, oh, if you flip it and you get the same molecule back, but you can't get from this one to that one, It really, the whole like handedness thing really does come into play, because it's like a screw or a propeller. You know, we're used to screws always being designed the same way, right? Righty tighty, lefty loosey. But they don't have to be. Screws are a chiral object. We by convention only use the right hand version of them. But there is the other version of them as well, where it would be lefty tighty, righty loosey. Another way for, how many of you have you've had calculus, right?
Yes.
Have you had calculus, have you learned about the right hand rule? I guess that's more physics.
Yeah.
Oh,
For
for
magnetism.
You know, magnetism. Screws. Everyday screws follow the right hand rule.
Yeah.
You turn it, you curl your fingers, the way you turn the screw, your thumb points the way the screw is gonna move. Just like magnetic fields.
Yeah.
But that's just by convention. We use the right-handed version out of convention. There is a left-handed version. If you've ever worked on bicycles, you know that one of the pedals is reverse threaded. So that it doesn't unscrew when you pedal your bike. It would be unfortunate. But it can be really frustrating if you don't know that and you're working on a bike for the first time. Like, why isn't this loosening? It's a left-handed screw. Anyway. When we start looking at drawing these products, until we get really complicated stereoisomers, and being really careful there, the easy ones are easy. The easy ones are going to be ones that look like this, and it can be typically what you have attached to your dienophile is electron withdrawing. So usually it's something else with pi bonds attached to it, just because that makes it more reactive. So cyano groups, nitro groups. Yeah, exactly. But really, anytime you've got a conjugated diene and you've got something else with a pi bond, your first thought should be Diels-Alder. Start with it, Trent, and we can. Sometimes it can be helpful to draw out your new cyclo group before you worry about your substituents. Okay, so we start with trans substituents, we get trans products plus the image. Just more practice problems. And again, it really doesn't matter what the substituents are. Although you will notice that all of these ones make it they're dienophile into a larger conjugated system. They're all electron withdrawing. With those resonance structures. You wanted to practice drawing the mechanism too. It's always 3 arrows. It's your 3 pi bonds that are moving. First pi bond moves towards the dienophile to make a new sigma bond. Dienophile pi bond moves towards the diene to make a new sigma bond. And to make room for that, and to fill the empty valence, the other side, your last pi bond moves over. We need. Plus the N in this one. We may need to a compound. Anything different if it's a carboxylic acid, that's your X's instead of an ester. Still cis, so we're still gonna make our cis product. And once again, because it's symmetrical. We gotta need some compounds. So, by the very nature of the Diels-Alder being a 4+2 cycloaddition. Meaning we have 3 pairs of electrons that are reacting, it's always gonna make a cyclohexyl group. Right, so you're always gonna get the same thing. The only question is the stereochemistry. All right, questions so far? I keep looking at that clock, even though I know it's wrong.
That's almost it.
It's a good enough time to mention. So lab, we're just gonna recrystallize and do melting points of a product from last week. And your last 2 assignments. So basically your assignment for that one is just write up what happened with the new material that you proposed. Did it work or not? And then give the results, and do they match with what you expected? Did the reaction progress the way we thought it should? And then your last 2 assignments are practice test and then lab final. And I'll have both of those ready for you in lab today. And again, lab final is just a synthesis practice. That we'll talk about in more detail there. And the practice final is just like for the midterms, just a practice test. So you get, instead of having a quiz this weekend, just work on that. Right, and I will double check our schedule. I think we're scheduled for a Thursday final, or is it Tuesday?
Tuesday. I mean, it doesn't matter.
I'll check that at break. I'll have this pulled up. But just so we have that on our radar, we only have 2 more new assignments left to do. Quarter went quick, didn't it? All right, so reminder, it has been a week since we did have that snow day. About the term S-cis versus S-trans. So S-cis, we're used to thinking about cis and trans in terms of cyclo groups or in terms of alkenes. S-cis and S-trans is referring to what part of the molecule? Anybody remember? The sigma bond in between the 2 pi bonds. Right, so because of the resonance, that sigma bond, even though normally we expect a sigma bond to be able to freely rotate, because of the resonance of the pi bonds, this sigma bond is kind of locked into either S or into cis or trans, similar to an alkene. Because in order for it to rotate, you have to break that resonance. So S-cis is referring to, is the sigma bond cis or trans? So this is S-cis. This one is S-trans. So because we need our pi bonds arranged to be pointed in the same direction. And we need if we're trying to turn 4 of these carbons into a new cyclohexyl group, they have to be pointed in the right direction, they have to be S-cis, not S-trans, or else it won't go through a Diels-Alder reaction. So out of these three, we have 1,3-butadiene. We have a conjugated diene, but it's locked in the S-trans conformer.
Right.
And then we have the opposite, we have cyclopentadiene, which is locked in the S-cis conformer. So which one is gonna be most reactive and which one's gonna be least reactive in terms of Diels-Alder?
Last one would be most reactive.
Yeah. Because this one's always S-cis. This one's S-cis some of the time. And this one's never S-cis. So least or even non-reactive in terms of Diels-Alder. We can't get that one to go through a Diels-Alder. And that means if we have one that's not locked into one conformer or the other, that sterics can play a role. Depending on what else we have attached here, if we have big bulky groups that are shifting their equilibrium constant. So that it might favor S-trans more than it would otherwise. So if you think of. So let's say we had, I don't know, a big a T-butyl group. On both of these, those are not going to want to be. In the S-cis conformation, right? Even though it's not technically locked into the S-trans, if I take this and flipped it over, I would have. Still a T-butyl group here, and then a T-butyl group facing the other way here, right? That's gonna be a whole lot more stable just based on sterics. Right, so. Even though this one, we couldn't say it's non-reactive, we could say it's a whole lot less reactive. Than just the regular 1,3-butadiene, it doesn't have these big bulky groups interfering with each other, and we could do the opposites as well. If we actually put the other T-butyl group here, they're not gonna interact that much. But they definitely are going to be able to be sort of further apart from each other. If we put it in the S-cis conformation, because then we wind up with. Actually, I think we can put it here. Then they could be actually facing opposite directions when they're in the S-cis. So we can actually we can tweak the reactivity a little bit by changing what's attached to our diene or our diene file for that matter. And just because we need more practice visualizing these in 3D. So cyclopentadiene will react with itself in a Diels-Alder reaction. You have one of your dienes acts as the diene and the other one acts as a dienophile. And we get what's called a dimerization reaction. It's a tricky one, huh? So we're actually going to wind up making a bicyclic structure. So if we picture this as being flat, bring our cyclopentadiene, I'm going to bring it from behind the board. We're going to make our new cyclohexyl. And so it's these two carbons are now right here. These two carbons are still connected across the middle. So if you visualize it, there's our original cyclopentyl group that acted as the diene. Which means these two carbons, which are still part of a cyclopentyl group. And that pi bond didn't react. Clean this up a little bit. We get this bicyclic structure fused to another cyclo group. And is that going to have stereochemistry?
Is it a double bond?
Yeah. This started cis, which means this is cis. Still have that other pi bond there. So we either have both. And again, the cyclohexyl part does look like it'd be meso, but because we have this leftover pi group here, we do have some asymmetry here. So we would also get this version.
Well, the kind of picture this is like the second one coming in from the top and the bottom. So would it push the, like on the left one, would it push the one carbon on the right down? It's coming in from the top.
This one.
Yeah, so like would they be opposite? Like instead of both coming out of the board,
So-
it'd be one down, one up?
Good question. In that, we need another term to describe that.
Yeah.
So with bicyclic structures, we actually have to, if there's two ways they could be arranged. Either with this other structure pointing towards the rest of it or away from the rest of it. So we actually get what are called endo and exo products. So endo means pointed towards itself, pointed inward. Exo means outside, pointed outside. So this is a more. This is not another cyclopentyl group, but you can picture if these things were connected. Like our last one, it's very similar to what we would get there. We either wind up with them pointed, this is called endo, because these ones, these substituents are both pointed towards the larger bridge part. They're either going to be pointed towards the small part of the bridge or pointed towards the large part of the bridge. I'd say the large bridge because there's two carbons across here versus one carbon bridging right here. So if we think of these two carbons as being constants, there's a bridge, a linkage between these two circled carbons two different ways. There's the two carbon route or the one carbon route. If you're pointed towards the two carbon route, you're pointed towards the larger part of the molecule. That's what makes it endo. You're pointed inward towards the large piece of the molecule. And if you're pointed towards the short bridge, then that's considered exo. And so it's a little bit tricky to visualize. And we do actually see both of them. Alright, and so if we start with it. With our dienophile, we have our dienophile trans. Then we're always gonna wind up with one of them endo and one of them exo. In this case, right, instead of thinking about one above the ring and above one below the ring. We got one pointed towards the large part of the ring, one pointed towards the small part of the ring. It's the same basic idea. So do you see how that connects to your question you were asking before? We always draw the bicyclic part the same way, because otherwise it gets too confusing to keep track of things. But either way. Our dimerization product here. Is either gonna wind up with the rest of this cyclopentyl group pointed towards the short bridge. Or pointed towards the long bridge. So you can get both the endo and they both have to be cis relative to each other because it's a ring structure. But we will get a mixture of both the endo and exo products.
So here you have four, because you have endo, exo, and for each one you have the two different enantiomers based on that reactive double bond.
So if we. Draw this out in this structure. We either wind up with our cyclopentyl group both down. Like that, or both up.
Yeah.
Those are your two enantiomers.
But the double bond, the cyclopentyl group at the very far right could be on the other. So it's gonna be right.
Yes, you're right, we would get more.
Yeah.
We'd get the both exo products and both endo products. Would be the other way to see the possibilities, right? So this is our endo, one endo product. Our other endo products, they're both still downward. But our pi bond is on the part facing towards us. And then we would have both exo products as well, where they're both facing. There's an exo product. The other exo product would be with the pi bond here. So more practice drawing bicyclics. We haven't practiced that in a bit. As you can tell by how sloppy mine started. Reminder with those. I find it easiest to start by drawing the V, the inverted V for the front part. And then draw your inverted V that's going to go to the back, and that kind of gives you your spacing. So it's a little bit easier to get everything oriented, less erasing that way, I found. But your mileage may vary, draw it how it works for you, how you can see things visually. If you wanted to just draw it as a cyclohexyl group with the bridge like that, that works too. It can just be a little bit trickier to see the endo versus the exo side. But for my money, this is actually a lot easier if you force one of the rings to be planar and then just connect the other parts. That's actually not a bad way to think about it either. It just doesn't show you the full 3D structure quite as well, the way that you're locked into that boat conformation. I'm just teaching the high schoolers in intro to Gen Chem. They're taking our we're just getting into Vesper geometries. And so I had to show them wedges and dashes for the first time, like blew their minds. Like,
Is there any limit to how big and how complicated molecules can get by doing this? No, but let me show you cyclohexane in the chair column. And I think I scared him a little bit, but.
That's good.
All right, let's. All right, let's finish up talking about the endo versus the exo, and which figure out which one is gonna be favored. And then we'll take our break. All right, so and you might be able to tell by the diagram here, this is mastering organic chemistry. Because I love the way that he draws transition states in particular, in orbitals. So in order for us to get this Diels-Alder reaction to work, we actually have to look at the individual orbitals in order to predict which stereoisomers are going to be favored. We have to look at the orbitals. So here's our two possibilities. Here's our endo transition state. Here's our exo transition state without orbitals. Seems like this one might be favored, or this one might be favored based on sterics. But if we look at the way that the orbitals all line up, and we actually see that both of them are valid to some extent, right? Because your diene HOMO is going to have one node in the middle. Your dienophile LUMO is going to have a node in the middle. Because we need them to actually be opposite phases because of the diene HOMO having one node in the middle. And the way we know that is if you remember thinking about these pi systems, is if we just looked at 1,3-butadiene, your pi system, your lowest energy pi system looks like this, right? And then slightly higher in energy, we would add one node in the middle. So it would look like this. And then there's a higher energy pi system that has two nodes in it, right? How many pairs of electrons does our diene have in the pi system? Should have two pairs, right? So that means we have electrons in this energy level. We have electrons in this energy level. We don't have electrons in the dienophile, or sorry, in the diene LUMO, right? That's what makes it the LUMO, lowest unoccupied. So we have our highest occupied energy level in the diene looks like this. You see there's a node in the middle where the shading switches from being top to bottom. They're out of phase. They switch phase in the middle of the molecule.
Wait, why did we have, because there's 4 electrons and 4 orbitals, why would we have them in the one with the one down?
So I didn't put this to scale here. I leaving myself room to draw the higher energy case. Basically, each one of these different variations where you have these p orbitals overlapping is an energy level, and each energy level can hold 2 electrons.
Oh, okay.
Just like orbitals, right?
Gotcha.
You didn't have me or Carl for Gen Chem, so you might not have gotten quite as much emphasis on, but remember s orbitals, p orbitals, and filling in those orbital diagrams with the arrows. It works the same way once they're hybridized to make these pi systems.
Okay, thank you for that.
Alright, so our diene HOMO has a node in the middle, so where it switches phase. Our dienophile LUMO has a node in the middle and where it switches phase. We need these 2 orbitals to interact in order to get these pi orbitals to turn into sigma bonds. We need these 2 to overlap, so they have to be in phase. And we need these 2 to overlap, so they have to be in phase. So basically, our transition state looks like these homos and lumos starting to overlap with each other, and it's kind of halfway in between a pi system and sigma bonds. They're starting to overlap. And we can see that both with the exo and with the endo. Right, both of them look valid from that point of view. Where it gets tricky though, is when you have these other electron withdrawing groups attached to your dienophile, they have pi clouds as well. And their pi clouds are going to want to arrange themselves so that your pi clouds are going to be helping fill in those lumos. Basically, you want your pi clouds to interact with the other pi clouds. So your endo transition state is actually favored kinetic. This is another case of kinetic versus thermodynamic product. The thermodynamic product is the exo product because there's less sterics. But your transition state is lower in energy for the endo. As long as you have pi clouds on your substituents on your dienophile, because having your pi clouds stacked with other pi clouds creates favorable interactions. And so endo is favored kinetically, exo is favored thermodynamically. As long as your other substituents on your dienophile have pi clouds. If your other substituents on your dienophile don't have pi clouds, this all goes out the window and it's just looking at sterics. Right, so here's what this looks like. So here's our what he's calling the primary orbital overlap, where we're making our new bonds. Here's the other pi clouds attached to our dienophile that can still have favorable interactions. Right, and you don't get those favorable interactions if you're putting your electron withdrawing groups in the exo position. They have to be in the endo position to get all of these pi clouds to stack up together. All right, that was a lot. So let's take a break and we'll come back and we'll do some practice with this. Let's come back at 10 after. Good. Yeah, and you know, it doesn't look like it outside, but it's almost baseball season. So they had tryouts. Not very many places in the US have to do tryouts in the basketball gym for Little League. But you know, it's the same 50 to 60 kids that are in all of the same sports together.
Okay.
So it's like they've been in, you know, they basically just mix and match from it's the same ones that were on the teams last year. But everybody, you know, you get a different coach every year, but it's a coach that you know because there's only 5 coaches.
Right.
And it's the same kids. Like, oh, okay, you're not going to be on your best friends team this year, but you're going to be on your second and third best friends teams because they weren't on your team last year, but they got drafted. I mean, so it's really, you know, it's the dad coaches drafting based on who they know and who you know, what parents they want on their team. Some coaches just draft based on the parents. So that's the big scuttlebutt in town among 5th and 6th graders this week is that the draft for Little League happened on Sunday night. And so everybody's figuring out who's on what team and, you know, always fun. And plus there's the 5th and 6th grade basketball playoff finals over at Kale Community Center are on Thursday. So my son's really excited for that because his team's still in it. They won a playoff game, which is always exciting. And so yeah, youth athletics is way more time consuming than I remember it being when I was a kid. I'm sure it was just as time consuming for my parents as it is for me. But as the kid, it didn't seem like it.
I think you're like on the field playing, time flies.
Right. Yeah, exactly.
Yeah, I remember it being just as long for my parents as it was for me.
Yeah.
I mean, especially from swimming, it's at least 3 hours of practice each
It's true.
day. So
When that part's only going to get worse as they get older and they go into everyday practices instead of like 3 days a week. But all right, it's really good, and I'm glad that my son is having as much action, and my daughter too are both really enjoying youth sports. I did not particularly enjoy youth sports until I got into some weird sports. I did because I was tiny as a kid, so I couldn't, you know, keep up playing baseball or football or basketball. So swimming and water polo was my sport, and wrestling because it was normalized by weight. And then I liked youth sports, but I had to find that little niche. So I'm glad that my kids are able to do well and have fun at the more mainstream ones because we don't have water polo up here. I know. I wish I would play a Masters League if they had a Masters League up here, but anyway. Oh, fencing. I can imagine.
Stab people with a sword.
All right, let me update. I got 2 things I can cross off my to-do list after our break. That was a very productive break for me. And I have to keep track of all these things now, or else I forget what I'm supposed to be doing. When all I had to do was teach, it was easy enough. Keep track. I have 2 classes, and I have to do these things for these classes and grade. And now I had 3 different mini meetings just on my way into my office this morning. Anyway.
You said the endo configuration on the last slide, that was favored thermodynamically. Right?
Endo is favored kinetically
Okay.
because it lowers the transition state energy is lowered by all these pi orbitals overlapping with each other in favorable ways. And in general, we're going to favor the kinetic product pretty much always with these Diels-Alder reactions. There is some amount of back and forth, but that difference in the sterics is a lot smaller in terms of energy. So the kinetics make the biggest difference when it comes to your leacher product. So endo product is favored as long as you have electron withdrawing groups, meaning other pi clouds and other lone pairs that are conjugated with your diene file, which is pretty much all of them. So if it's trans, does it matter? You're gonna get one endo and one exo regardless, right? So you still might wind up with two enantiomers, but you're not gonna get a major product that's both endo or both exo. So we don't need to worry about as much as long as your dienophile is trans. When your dienophile is cis, or when you only have one thing attached to your dienophile, you need to go to the endo product. And so our endo product in this case. So start by drawing your bicyclic structure. Again, there's our cyclohexyl group that we just made with our alkene bond that's still left over. We have two cyano groups that are both going to be in the endo configuration, which means pointed towards the remaining pi bonds, towards the larger part of the molecule, which means down. No plus En there because it's a meso compound we just made. We will get some amount of the exo product with this, with the cyano groups pointing upward, but the major product is gonna be this. And so some of these, the diene looks a little bit different. So for instance, this is a furan rather than just a cyclopentadiene, but it's still a diene, still a conjugated diene. But we're still gonna make our bicyclic structure here, just with an oxygen as your bridge across the top. And then because these are trans, we'll get one down and one up. In this one, I would be careful with just putting plus En because there's a lot of stereochemistry going on here. So rather than writing plus En, because we don't actually want to flip all of the stereo centers, we just want to flip these two. So I would just redraw it. So we drew the back one up and the front one down, so then switch that. Also, all just goes to show that even when it seems like the mechanism is relatively straightforward and there's only one way we can look at it, there's still more ways we can look at it. So proceed, we only have one substituent on our dienophile. It does have pi clouds a pi cloud associated with it, so we're gonna favor the endo product, but there's two endo products. So we still wanna be careful about how we draw this.
Seems like the safest bet is to draw it out, whatever name.
When in doubt, when you're not sure how many stereo centers you have. Just draw them out rather than plussing in. So in this case, we have a bicyclic where we're gonna have, it's gonna be endo for our major products, but we can have endo on the back carbon or endo on the front carbon are our two possibilities here. And that one is the enantiomer. If you think about this first molecule, think about putting a mirror behind it. If you put the mirror behind it, you get that. Everything in the same position except where you position those two, but I'm always wary of that when there's more than one stereo center. So like you said, when in doubt, just draw both possibilities.
It could be like a weird thing where the carbonyl double bond reacts to the.
There's still some possibility. It's not gonna, the carbonyl is not gonna react as a dienophile. Because the difference in electronegativity between the two sides means you get a partial positive and partial negative.
Okay.
So the carbonyl will react, but not via Diels-Alder.
Okay.
Diels-Alder, the dienophile has to be relatively symmetric in terms of electronegativity. In order for it to work.
Okay, so we have like, instead of CN on either side, we got CN on one side, and like just a hydrogen on the other side, that would be less reactive.
It would be. We still would see that. We have that right here, right?
Yeah.
It would still react as a dienophile because these two are still both carbons. It might affect the rate though.
Yeah.
But that's why we don't have, like, this carbon to nitrogen also has 5 bonds. We don't have them drawn, but it's a triple bond. So, but that's not gonna react the same way these will, because the fact that it's two carbons, even though that one side of it's got a little more electron density than the other. The fact that they're both carbons is what allows the Diels-Alder reaction to really work. And even the other cycloaddition that gets used all the time was that same, remember the asymmetric epoxidation, sharpless? The other reaction that he studied, that he's known for, that won in his second Nobel Prize, is another cycloaddition. That click reaction. But even this is not really. It still relies on the fact that, yeah, all three of these are nitrogens, which means they're all relatively equal in electronegativity. And these two are carbons, which means they're relatively close in electronegativity. So for it to be, for the cycloaddition part to work, your two pieces kind of have to be similar in the way that the electrons are distributed. Or else it doesn't go through this pericyclic mechanism. Does that make sense? And actually, this one works better with alkyne anyway. But it still winds up being a 4+2 cycloaddition. Is it a 4+2 or is it a 2+2? Get those electrons move over. No, the other way. There's a lone pair here. Those electrons move over. Those electrons move over. Those electrons move over. You still wind up with it being 4+2, yeah. You break 2 pi bonds and make 2 sigma bonds. So it's really similar an overall structure to a Diels-Alder. All right, let's do F. Is the last one here. Because that's the most complicated one we have left on the board here. It has gonna have a lot of leftover ring structures. So it's still gonna be these electrons come over here, these electrons come over here, these electrons move over. We're still gonna make that bicyclic structure. Again, with the oxygen in the middle, though. We just have this leftover ring structure, which is going to be in the endo conformation, which means pointed downward. And again, you might see some of the exo, but it's going to be less favorable because you lack that pi interaction. Organic chemists don't celebrate Pi Day because every day is Pi Day. We're always worried about Pi. All right, questions on this last one? Okay, I think we're gonna wind up having like a half a lecture. I did check on our schedule for next week. We do have our final on Tuesday. Of next week, regular time slot right in here. So on Thursday, whatever we don't get through, there's a couple more concepts. We're not gonna spend a ton of time on sigmatropic rearrangements, but the electrocyclic reactions wind up being kind of important. And kind of ties some of these orbital ideas together. So I want to make sure we get enough time to talk about that. We still have like half an hour in here that we'll go over them once, but then we'll probably have like a mini lecture, half an hour on Thursday, where we go over that stuff again. We'll kind of finalize some of the ideas for it. Then the rest of Thursday will be review, time to work on your practice tests, ask me questions, go over more examples, that kind of thing like we've done before. But having lost last Thursday, we will use a little bit of time on this coming Thursday to finish up the material. All right, so the other classes of pericyclic reactions, the big one is electrocyclic. An electrocyclic reaction happens anytime you've got a conjugated diene or a conjugated polyene, which is exactly what it sounds like. It doesn't have to be a diene, you can have a conjugated triene. If you have a conjugated polyene, and it can actually go through a cyclization. And it's still 3 arrows, all 3 of your pi bonds or all of your pi bonds wind up moving. You wind up losing a pi bond to make a sigma bond. So very similar to Diels-Alder, but where it's different is that these electrocyclic reactions, usually it's happening within the same molecule. So this is an intramolecular reaction, or almost like a rearrangement, except it's rearranging the electrons, not rearranging protons or methyl groups. In some cases, there's a reason why we don't actually see this as a common molecule, because if you actually put this molecule, synthesize this triene, 1,3,5 hexatriene, it'll actually spontaneously form into cyclohexadiene.
And it's favored at equilibrium. 1,3-butadiene though will go through some amount of electrocyclization, but a lot less because you'd be making a 4-sided ring. And 4-sided rings we know are not very stable because of onyx, right? So. And here's where this gets really interesting and why it's worth spending the time on. And we're going to use cyclo or the hexatriene a lot as our example. If you actually have this triene, conjugated triene, that's substituted, in either case, let me get this so it'll fit all on the screen here. In either case, you're going to make a cyclohexadiene. However, there we go. If you catalyze this reaction with heat, you get one stereoisomer. And if you catalyze it with light, you get the opposite stereoisomer. And not just the enantiomer, you either wind up with them, you can wind up with them both being cis or have them be trans, depending on whether you catalyze the reaction with heat or light. And so that was kind of the first clue that the orbitals in that frontier orbital idea of HOMO and LUMO are going to play a role here, because heat versus light, if you're using heat, usually that means you don't have enough energy to excite electrons into the LUMO. But if you're using light to catalyze something, it's either going through a free radical mechanism or you're exciting electrons into some other type of orbital. Right, so the fact that we get different stereoisomers for these means we have to be paying attention to the orbitals. All right, and so note that the start with these two methyl groups both facing outward. And if you just catalyze it with heat, they sort of, when you bring these two carbons together, both of the methyl groups sort of rotate the same direction, or they rotate towards each other to both be facing out, or they can react both rotating. My arms don't rotate that way, but you can picture how I'm rotating in the methyls rotating into the board. But basically what's happening is these pi bond orbitals, just like we saw with the Diels-Alder, we need these pi orbitals to overlap to make a new sigma bond. And that means it's going to drag these methyls with it, because these pi bonds are parallel to each other initially, right? My thumbs are the pi bonds. If we want these two things to rotate towards each other to make a new sigma bond, you have to rotate the whole carbon in order to do that too, which means whatever's attached to the carbon comes along for the ride. So picture the methyls sticking out of the backs of my hands right now. They're facing in opposite directions. As I bring my thumbs together to cause that orbital overlap, that brings the methyls with it. And now they're both facing the same way. But if they needed to rotate opposite directions, if they were out of phase, then one of my thumbs would rotate in and one of my thumbs would rotate out. And that's going to bring the methyls into the trans configuration. So basically, getting the orbitals to be in phase versus out of phase is going to determine which way the substituents rotate. And that's why heat causes them to rotate one way, because that's, if you're catalyzing it with heat, that means you're starting from the HOMO. If you're catalyzing it with light, you're starting from the LUMO.
The electrons in the HOMO got excited to LUMO.
To the LUMO, exactly. Right, so heat means HOMO, light means LUMO, and we'll show the figure of this here in a second. Alright, so if you look at. A cycle or the hexatriene. Your lowest energy state is all of your p orbitals. With the same, with no nodes. So 6 of them in a row, so lowest energy. They're all in phase with each other. And remember, every time we add a new energy level, we add a node. Right, so we can fit 2 electrons in there out of our 6 that are in the pi system. If we add a node in the middle, we still have 6 p orbitals in every case. When you add a node in the middle, that's just the point where it switches phase. So that's an energy level that's got 2 electrons in it. Do it again. Still 6 p orbitals. Now there's 2 nodes, and it doesn't really matter where you put the nodes. By convention, you try to make it so that you have as much constructive overlap as possible and make it symmetric. But it's not going to matter for our final result. So here's our HOMO. Because that's the 3rd energy level that we can have, and we have 3 pairs of electrons to fill. And our LUMO is going to be 1 step above that. I know I'm drawing kind of small because I ran myself out of room here, but it's a small class, so hopefully everybody can see it. So now we added no nodes, 1 node, 2 nodes, now we need 3 nodes. So again, it doesn't really matter because all it matters is that we show the phases switching. And that doesn't have any electrons in it. So that makes this our LUMO. Lowest unoccupied molecular orbital. And this is our HOMO, our highest occupied molecular orbital. So if the HOMO looks like this, you ever see the connection between what I have drawn up there and this picture here? Then when we draw that out so that we have it in that hexagon shape, we want to take these 2 pi orbitals at the end and we want to overlap them so that either blue matches with the blue or the red matches with the red. Either way, we have to rotate them. So the thumbs are the blue at this point. They have to rotate like this, or they can rotate the other way as well to get the red to overlap. But either way, we just have to track the methyl groups that are attached there. So we're going to rotate the blue towards each other. Both of the methyl groups are going to get dragged upward in order to do that. If we rotate it so that the red we're going to overlap, both methyl groups get dragged downward by that rotation. Either way, we get the cis product. All right, and so a lot of times rather than draw this gets kind of complicated to draw every time. If you can see this, then the shorthand is a lot of times we'll say, well, it doesn't really matter what the rest of the orbitals look like in there. It matters is that they were in phase at the end. It matters which direction the blue was facing at the end. So both of these for our HOMO, the blue was facing up on the ends, on both ends. Which means in order to get them to overlap, we need to rotate 1 clockwise and 1 counterclockwise.
So they refer to that as disrotatory. Because they're rotating in opposite directions. And when you do that, if you rotate it in the disrotatory way, both of your methyls get dragged downward. If we catalyze it with light instead, it's actually going to be the LUMO reactant, not the HOMO. Which is if we catalyze it with light, we have 3 nodes. And it means that our phases at the end are opposite from each other. Blue up versus blue down. And to get blue up versus, if we are still trying to get the reds to overlap, they just picked red conveniently. It doesn't matter though, either blue or red. We're trying to get the 2 reds to overlap. So now if my thumbs are the red, to get them to overlap, they both need to rotate the same direction. So they call that conrotatory. Because the way that's drawn here, they're both going to be rotating counterclockwise, or they could both rotate clockwise, but they have to be rotating the same direction. Which means if you start with your methyls facing outward, one rotates counterclockwise, that drags the methyl down. The other one rotates counterclockwise, that drags the methyl up. So this applies to larger and smaller pi systems as well. The same idea of you need the carbons at the end of the chain to rotate so that you get constructive interference, so that they're in phase with each other. The tricky part with that means it's really hard to generalize because there's a lot of ways that you can have this happening, right? If it's 4 electrons in the pi system instead of 6 electrons in the pi system, then your HOMO looks a little different, right? If you start with your methyl groups both facing in compared to both facing out, or 1 in and 1 out, that's all going to change things as well, right? If you had 8 electrons in your pi system instead of 6 electrons in your pi system. So I always come back to this. Figure out what your HOMO and your LUMO are going to look like. And then figure out what that means as far as how do I have to rotate them to get them to overlap properly. All right, so there are a set of rules though, called the Woodward-Hoffman rules. And Woodward won a Nobel Prize for starting to explain this process, and then Hoffman won a second Nobel Prize almost 20 years later for finalizing some of these ideas in terms of the orbitals, bringing together. So you might know, you probably don't remember, but remember Kenichi Fukui, the Japanese scientist who won a Nobel Prize for frontier orbital theory. He won it in 1981. So Hoffman actually shared the Nobel Prize with Kenichi Fukui because Hoffman basically used Fukui's ideas about frontier orbitals and applied them to Woodward's rules. Woodward wasn't able to explain this because he didn't have the ideas of frontier orbitals yet. So Woodward said, well, I'm observing that there's this difference between heat and light when we catalyze these electrocyclic reactions. But he couldn't fully explain it until Hoffman and Fukui did their work to kind of close the circle. Right, and so, again, I don't like. To me, this is more confusing than the whole process, because this is just kind of giving you the end results. And it's limited, because what about 8 pi electrons? Basically, you can generalize with these. If you have an even number, you'll notice that it kind of alternates back and forth, right? If you have an even number of pi bonds of electron pairs, then it's always going to follow the same rules as 4 pi electrons and 8 pi electrons and 12 pi electrons will all have the same general rules, because it's just going to flip-flop and alternate back and forth. And if you have an odd number of pi pairs, then it's going to work the same way. So if you have 6 pi electrons, it goes this way. If you had 10 pi electrons, it would look the same as 6 pi electrons, right? Because it's all about odds and evens. But to me, that's almost more confusing than drawing these out. And one of the mechanism questions on this test, instead of being a true mechanism question, it's going to be, I'm going to give you a situation like this. Say, explain using orbitals. Which stereoisomer are you going to see? So, and the way that I would recommend doing it is build this up. Find which one's your HOMO, which one's your LUMO. Look back. Okay, it says light. That means it's my LUMO. How do things need to rotate to get that constructive interference? And again, maybe it's because I come from the quantum world and thinking about HOMOs and LUMOs makes a lot of sense to me. Based on you know what I studied in grad school, but that feels a lot less like memorizing arbitrary set of rules than this table. And it gets, then you can apply it to other ideas. The whole idea of HOMO versus LUMO and light catalyzing versus heat catalyzing starts tying a lot of other things together once you get a handle on this, which is why we're spending so much time on it. All right, so when we start, so this will be the last slide that we go over today. Let's see how much time I have. I have 6 minutes. Forming the cyclone is exactly what we've been talking about. It doesn't matter what else is attached to it. It just matters your starting positions and is it heat or light. So in this case, heat. Heat means HOMO. And we come over here and we look at, okay, we have 3 sets of pi electrons. 3 sets of pi electrons means that this is what our HOMO is going to look like. So the orbitals that are on the ends are already facing the same direction, right? So if we're looking at the ends here, we have this, the rest of this ring structure and everything else that's attached to it. Doesn't matter that that's even there, right? It's not reacting. So we have to draw it in our product. But the main thing is, starts with both of our R groups facing outward. And so to get these to overlap with each other, it's going to be disrotatory, which means our R groups are going to be cis relative to each other. The other trick with these is to remember that, yes, we're making a new sigma bond right here, but that also means our pi bonds are gonna shift over one spot. Just like with the Diels-Alder reaction. The last thing then. What about when we have them do the ring opening reaction instead of forming the ring? So undoing. They're starting with the orbitals already overlapped. And if we're using heat, we're trying to get to the HOMO instead of starting from the HOMO to overlap. So everything works the same way as far as con-rotatory and disrotatory. We just have to like, okay, well, we're gonna take this and we're gonna make it a conjugated diene with these ethyls. But if we started with our orbitals overlapping and we're using heat to make 2 pi electrons, our HOMO is gonna have 1 node. And so the other connection you can make, so you don't have to redo this every time, is your HOMO always has 1 fewer nodes than the number of pi bonds. And your LUMO has the same number of nodes as pi bonds. And so in this case, we're trying to make something with 2 pi bonds, which means the HOMO has 1 node. So we're trying to make it look like that. And if we're starting with the shaded parts overlapping, and we want the shaded parts to be pointed in opposite directions, it's got to open by being, let's see, it's hard to visualize, but I think that's, yeah, they're both counterclockwise, right? So that's con-rotatory. In other words, this is going to open that way. So that's going to leave our ethyl group pointed up. This one's going to, if this one rotated up, this one has to rotate down, which is going to bring our ethyl group inward. And honestly, I've not found better ways to demonstrate this than thumbs and rotating them. It actually works. You get the hang of it. So on your test, don't be afraid to sit there and look at your thumbs and twist your hands. All right, so we'll do these other practice problems and talk very briefly about sigmatropic rearrangement on Thursday. All right, so lots of practice. If you come in on Thursday having tried some of these, then we can, you can figure out where you're getting hung up on your understanding. And we can walk through it, but either way, we'll walk through these practice problems because I expect this to be one of the trickier concepts that we've covered since the midterm. It takes the most practice in visualization. Anyway. Any questions before we end for the day? Lots of process.
Probably no questions later, but.
That's great because you have Thursday and you have lab. All right. Then let me end the recording and again I'll have we'll also talk in lab about your final lab project and your practice test as well.